Hello and welcome. Today we are continuing with the day 3 questions. We finished in the last video the MCQ questions. Now we have the FRQ questions for day 3. As always saying, try to master all the questions of day 1 and 2 and try to be a little bit fast in finishing all the files. We have 30 days content spread over 60 days. So you have a chance if we are missing one day to do the other day the missing content. The first question FRQ is asking, so SO2 phase draws a resonance structure for SO2 molecule. Explain how the actual SO bond length compared to the standard SO single bond and the standard SO double bond. So let's have a look how I will draw this structure. All right, so FRQ1 asks us to draw the resonance structures for SO2 and explain how the actual SO bond length compares to a standard single and double bond. Let me walk you through this step by step. First, let's draw the two resonance structures. Sulfur is our central atom because it's less electronegative than oxygen. In the first structure, I will put a double bond between the sulfur and the left oxygen. So remove these two electrons and put a double bond here and a single bond to the right oxygen. Don't forget, each oxygen needs its lone pairs to complete the octet. The left oxygen with the double bond gets 2 lone pairs, and the right oxygen with the single bond gets 3 lone pairs. Sulfur also has 1 lone pair. Now for the second resonance structure, it's basically the mirror image. So the double bond is now on the right oxygen, and the single bond is on the left oxygen. We connect these two structures with a double-headed arrow to show they are resonance forms. So this one will have the same lone pair. Now this one has 6 electrons, and this one has 4 electrons. Here is the critical point, and this is worth a point on the AP Rubric. The actual molecule is not flipping back and forth between these structures. The actual bond is an average or a hybrid of both resonance forms. Now let's calculate the bond order. This is the key to understanding the bond length. In structure 1, we have 1 double bond, that's 2 bonds, and 1 single bond, that's 1 bond. So the total bond is equal to 3. So 1 double bond and 2 1 double bond equal 2, and 1 single bond equal 1. So the total bond is equal to 3 bonds. The total bond is equal to 3 bonds. Now, how many locations can this bond be in? They can be here or can be here. And even in the other molecule, it can be here or it can be here. So this means it can be over 2 different positions. So I have 2 different positions. So the bond order equal to the total number of bonds divided by the number of locations. So 3 divided by 2 equal to 1.5. A bond order of 1.5 means the actual SO bond is an intermediate between the single and double. It's not single, it's not double, it's something in between. So think about it this way. A single SO bond is longer and weaker. A double SO bond, which is S double bond O, is shorter and stronger. The one that we have in our structure, the actual SO2 here, is something intermediate between them. So the length between it is in between them. It is shorter than the single bond, but longer than the double bond. Even the strength, it's stronger than the single bond, but weaker than the double bond. So let's make sure we hit all the rubric points. We draw 2 resonance structures correctly, state the actual bond in average or hybrid, 1.5, and explain the bond length is shorter than the single but longer than the double. Mention the bond strength is intermediate between the single and the double. That's 4 points, and we move on. Second question is asking about to draw the Lewis structure for CO2 and carbon monoxide. Then use the formal chart to explain why CO is more reactive. This is classic question about molecular stability. So let's draw CO2. Let's start with the carbon dioxide, the CO2. Carbon is central, 2 valency electrons, and carbon total valence electrons equal to 4 plus 12, that's equal to 16, right? If you want to draw it, you put C in the middle, and then oxygen and oxygen, and you make one bond. So how many electron pairs here? I have 16 divided by 2. If you want to get the number of electron pairs, divided the number of electrons by 2. You get 8 pairs. I have already one pair here and one pair here. And this is the second pair. So a third pair, 3, 4, 5, 4, 5, 6, 7, 8. So 8 pairs, but this does not achieve the octet. So if I put a double bond to both oxygens, so I move this and make it as double bond, and move this and make it as double bond. Each oxygen get only 2 lone pairs. Let me verify with the octets. Carbon has 8 electrons around it to form 4 bonds. Each oxygen has 8 from the double bond plus 2 lone pairs. That's perfect. Now let's calculate the formal charge for the CO2. The formal charge calculation, this is crucial. The formula is how to do it. So formal charge is equal to the number of valence electrons. So the number of valence electrons, and this is fixed number. It comes from the group number, which is 6, which is 4 for the carbon, and minus the lone pair electrons, minus plus the bonds. So for the left oxygen, let's do it for the left oxygen. 6, because this is the valency, minus 4. Let's see, draw the double bond. When we draw the double bond, this one disappears and this one disappears. Okay, so I have 2 lone pair of electrons. So I have 4 electrons. And how many bonds? I have 2 bonds. That's 6 minus 6 equal to 0. So the oxygen on the left has 0. For the carbon, it has 4 valency minus no lone pairs plus 1, 2, 3, 4. So 4 bonds, that's equal to 0 also. And the other carbon is like the left one, 6 minus 4 plus 2, that's equal to 0. So all formal charges here is equal to 0. This means that carbon dioxide is very stable compound. Now the carbon monoxide. Carbon monoxide, this is trickier because carbon and oxygen, total valency electron is equal to 4 plus 6 equal to 10 electrons. To satisfy the octet, we need a triple bond here. So it's carbon, triple bond, oxygen. The carbon gets 1 lone pair on the left, oxygen gets 1 lone pair on the right. We cannot have 2 lone pairs because this will be more than 8. We have 1, 2, 3, 4, 5, 6, 7, 8. Now this is correctly done. Calculating the formal charge for the CO. Formal charge for carbon is 4, which is the valency, minus lone pair electrons is 2, minus 3 points. 4 minus 2 plus 3, which is 4 minus 5, that's equal to -1. What about oxygen? The valency is 6. The number of lone pair of electrons is 2. Take care in the bond pairs, I don't take the number of electrons, I take the number of bonds. So 6 minus 5 equal to +1. So the carbon is -1, the oxygen is +1. Here is the key difference. Carbon monoxide has non-zero formal charges. So carbon is -1 and oxygen is +1. Why does this make CO more reactive? Listen carefully. This is worth the justification point. Molecules with formal charges are less stable than molecules with 0 formal charges. Very, very important to know that. So CO has formal charge, seeks to react to reach the 0 charge state. While the molecules that have 0 formal charges are more stable. The molecules with formal charges not 0, energetically unfavorable. These molecules seek to react to reach the 0 charge state, a more stable configuration wanted to be. So CO2 is already at 0 formal charge. It is happy, stable, unreactive. CO has formal charges creating instability. It wants to react to get rid of them. That's why carbon monoxide is so reactive and dangerous. It really reacts with the hemoglobin in your blood, for example, and it's a very toxic gas. So let's check the rubric points. I drew the CO2 correctly with all the formal charges. I drew the CO very correctly with the formal charges also, CO, not CN. O correctly with the formal charges also done. Justify that non-zero formal charges means less stable, and connected this to a higher activity, and that's all done. 4 points secured, and next. Question number 3, FRQ. The FRQ3 is about acetylene, that's C2H2. We need to state the hybridization of carbon and identify the total sigma and pi bonds. This tests whether you really understand bonding. So let me draw acetylene that first. So I have H, C, triple bond, C, H. This is a linear molecule. Part A states the hybridization. Part A asks for hybridization of carbon. Here is a simple rule that makes this easy. Count the electron domains around the carbon atom. So I have this carbon is bonded to one hydrogen. That's one domain. It's bonded to other carbon with a triple bond. But here is the trick. Regardless, take care, very important. Regardless whether it is single or double or triple, it counts as one electron domain. So this one has around it. Most of the people are confused when they are asked. I have to focus on one atom. So look at this atom and look at the electron domains around it. It has two electron domains around it. Even if this is double or triple or single, it's counted as one electron domain. So one and one, two electron domains. Each carbon has two electron domains total, one from the CH bond and one from the C triple bond. Two electron domains means 2 minus 1 equal to 1. So SP hybridization. SP hybridization. The geometry is a linear shape with 180 degrees, with 180 degrees bond angle. That's it. SP hybridization gives us the point. Now part B, sigma and pi bonds. Now part B, count the sigma and pi bonds. You need to know the rule. Every single bond is just one sigma bond. Every double bond is made from one sigma bond. The first bond is usually sigma and one pi bond. What about the triple bonds? The triple bond is made from three bonds. The first one is one sigma bond. The other two are two pi bonds. So usually the first bond, so if you have this one, the first bond is usually sigma. If you add one more, it is pi. This is pi, and this one is sigma, and the third one is pi. So two pi's, and this one only is sigma, the strong bond. So the HC bond on the left, that's a single bond, so it is sigma, and this one, the triple bond in the middle, that's one sigma and two pi, and here this is sigma. So I have total sigma bonds are one sigma. First one here is sigma, and third one here is sigma. So I have total of 3 sigma, and these two are pi. So these two are pi. So I have 2 pi bonds. So let me say it again. This is SP hybridization, 2 electron domains, SP hybridization, 2 CH bond, that's sigma. So this is the CH bond, and this is CH bond. This is 2 sigma, and the triple bond is made from 1 sigma and 2 pi bonds. So these yellows are 2 pi bonds and 1 sigma. So what is the total? I have the total 2 and 2, 2 and 1. So it is 3 sigma bonds total and 2 pi bonds total in the compound. So the rubric bonds, let's review the rubric bonds. Identified SP, done. And identified, only we said that it's a linear shape. Identified 3 sigma bonds with correct breakdown. Identified 2 pi bonds from the triple bond. 3 points total and done. So FRQ number 4. Draw, if is asking us to draw PCl5 and NCl3, then explain why phosphorus can form PCl5, but nitrogen cannot form NCl3. This is all about the expanded octet concept. So first, let's draw PCl5. Phosphorus is central with 5 fluorines around it. So I have 1, 2, 3, 4, 5 fluorines around it. The geometry, if you have one central atom and 5 atoms around it, do you have any lone pair of electrons or not? Let me check. Let me check if there is any lone pair of electrons or not. I have one phosphorus which has 5 electrons, and I have 5 fluorines. 5 fluorines, every one of them is 7, so because group 7, so 35 electrons. So I have 40 electrons in total. 40 electrons divided by 2 is equal to 20 pairs of electrons. This is the first pair, second, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and there is no need for any lone pairs. Whenever you have a central atom represented by A, so any atom which is central, and five peripheral atoms without lone pair, what is the shape of this one? This is trigonal bipyramidal. So trigonal bipyramidal, 3 chlorines in the equatorial plane and 2 in the axis position. So here is what's important. Phosphorus has 5 bonds. Each bond represents 2 electrons. So that's 10 electrons around the phosphorus atom. That's more than 8. It's an expanded octet. It's an expanded octet. Remember, we said that elements in period 3 in the last session. I said elements in period 3 can have extended octet. They can have more electrons than 8 and they will be still stable. While if we draw the NCl3, so let's draw the NCl3. Now nitrogen with 3 chlorines and 1 lone pair of electrons on it. It has a trigonal pyramidal. So this is trigonal pyramidal. The other one was trigonal bipyramidal. This is one central atom, 3 atoms around it, and 1 lone pair of electrons. Nitrogen has 8 electrons around it, so 3 bonds plus 1 lone pair. It follows the octet rule. Why can't nitrogen make NCl5? So let's see why phosphorus can make PCl5 and nitrogen cannot make NCl5. This is $1 million question, and you must mention d orbitals to get the point. Let's explain it with the periodic table. So let's have a look at the periodic table and see how can the periodic table help us explain this one. Why the nitrogen is different from the phosphorus? Why the phosphorus we can make PCl5 but nitrogen no? Look at the periodic table. Nitrogen is in the period 2. Nitrogen is in period 2. Available orbitals for period 2 elements are either 2s or 2p. That's it. There is no d orbitals here. There is no d orbitals here. Available in the second energy level. Phosphorus is in period 3. This is period 3. Period 3 has 3s and 3p, and it has also 3 d orbitals available. So here is the key. To exceed the octet rule and have extended octet, to have more than 8 electrons, you need d orbitals to accommodate these extra electrons. If you want to have more electrons, and you have 2s and 2p only, like in the nitrogen. So where you will put the extra electrons? Where you will put? You have a maximum of 8 electron places, right? You have 2s and 2p. This can carry 8 electrons in the 2s and 2p. If you want to add extra 2 electrons, where you will put them? We don't have a 2d. We don't have a 2d. So nitrogen is stuck at the 8 electron maximum because it only has s and p orbitals available. Those can have only 2 plus 6 equal to 8 electrons max. While the phosphorus can expand. The phosphorus can expand. Why? The phosphorus has 3d empty orbitals. This allows it to form 5 bonds, right? It allows it to form 5 bonds. So if the phosphorus has 2 electrons in the 2s, has 3 in the 3s, has 6 electrons in the 3p, but what if it has 2 more electrons or 4 more electrons? It has the whole 3d empty. So if there is even more than 8, it accommodate 1 more, 2 more, 3 more, 4 more, can accommodate up to 12. Even more electrons it can carry. It can carry more electrons because of its empty 3d orbital. This allows it to form 5 bonds and hold 10 electrons. So the word that you want to hear, the bottom line, the period D and plus. So period 3 and plus, anything at period 3 or more, 3, 4, 5, can expand their octet by utilizing the d orbitals. Period 2 elements like nitrogen cannot because they have no d orbitals available. So let's check the rubric verifications. We draw the PCl5 correctly showing trigonal bipyramidal. We stated nitrogen in period 2 with no d orbitals. We stated that phosphorus is in period 3 with empty d orbitals available for extra electrons. And we justified that any element in period 3 or more can expand octets using the d orbitals, and that's done. Let's see the next question, which is FRQ 5. The FRQ 5 asks why the bond angle in H2O is 104.5 degrees. It's smaller than the bond angle in NH3, which is 107. This is testing your understanding of the lone pair repulsion of the VSEPR theory. Let's draw both molecules. The first molecule is water, oxygen in the center with 2 hydrogens and 2 lone pair of electrons. Ammonia, nitrogen in the center with 3 hydrogens and 1 lone pair of electrons. First point for the rubric. Both molecules are based on the tetrahedral geometry. So basically there is 4 electron clouds in both of them. So the geometry of the molecule is tetrahedral. Let me explain what I mean. Water has 4 electron clouds total, or electron domains, 2 bonding pairs and 2 lone pairs equal 4 domains. 4 domains means tetrahedral electron geometry with ideal angles of 109.5 degrees. Ammonia also has 4 electron domains, 3 bonding pairs and 1 lone pair equal 4 domains. Also tetrahedral electron geometry with 109.5 degrees. But why the different angles? Why it's not 109.5? This is where the lone pairs come. Here is the critical concept, and you must state this. The lone pair takes up more space than the bonding pair. You see the space that's taken up by the lone pairs and the space taken up by the bond pair. The space taken up by the lone pair is more than that by the bond pairs. They repel other electrons pairs more strongly than the bonding pair repel each other. Why? So the fight between these two is very strong fight that they push. It's like the gangsters push these two guys weak here. But the fight between these two is a little bit weaker, so the greens cannot push against the reds. If they are able to push against the reds, then it would have looked like that, right? The hydrogens will come up. But because the reds are stronger, so they are gonna push them down and make the shape looks like the normal water molecule like that instead of being up. So ammonia has 1 lone pair. That 1 lone pair pushes down on the 3 nitrogen to the hydrogen bond, compressing the NH angle slightly from 109.5. So the pushing here is by 1 gangster only. So the pushing is a little bit weaker than the pushing which is done by these 2 gangster lone pairs. Water has 2 lone pairs. These 2 lone pairs take up even more space and repel the bonding pairs even more strongly, squeezing the HOH angle down further to 104.5, while here only 107. So we have a pattern. More lone pairs equals smaller bond angle. CH4 with 0 lone pairs, for example, is also tetrahedral, right? But it has no lone pairs. That's why it's perfect tetrahedral angle 109.5. NH3 with 1 lone pair 107 degrees, slightly compressed. H2O with 2 lone pairs 104.5 degrees, most compressed. So justification that we must write. Let's make the statement clear for the AP examiner. We will say that the lone pairs occupy more space and triple bonding pairs more strongly than the bonding pairs repel each other. So the repulsion between 2 lone pairs is stronger than the repulsion between lone pair and bond pair, which is stronger than the repulsion between 2 bond pairs. So the answer depends on the lone pair space and the repulsion. Again, the lone pair electron clouds are larger and repel the bonding. Let's do it with red and or with the yellow, because we said it's yellow at the beginning. The lone pair electron clouds and the bond pairs are little repulsion than the lone pairs repulsion. So let's check the rubric. I have stated both are based on tetrahedral geometry. I identified H2O has 2 lone pairs and H3 has only 1, and justification about lone pair space and repulsion done. Question number 6. Boron trifluoride is a molecule and NF3 is a molecule. The boron trifluoride is non-polar, but nitrogen trifluoride is polar. Justify this difference based on the geometry. So let's say, let me draw the boron trifluoride first. Boron is central with 3 fluorines around it. Boron has only 3 valence electrons, so it forms 3 bonds with no lone pairs. It is deficient, it has less electrons than needed, so it's even not able to make octet. It's not even able to make octet. 3 bonding domains and 0 lone pair means trigonal planar geometry. All the 3 fluorines are in the same angle, so 360 angle is divided into 320 angles. Divide 360 by 3, you will get 120, 120, 120, separated by exactly separated 120 angles. This is perfectly symmetrical shape. While NF3, now the nitrogen trifluoride has 5 valency electrons, right? So 3 go to the bonding with the fluorines, and 2 remain as a lone pair. Draw it perfectly like that. 3 bonding domains plus 1 lone pair equals 4 electron domains, not 3 like here. The molecular geometry is trigonal pyramidal, like a pyramid with the nitrogen at the top and the 3 fluorines forming the base. It looks like the pyramid, like that. So trigonal pyramidal, not trigonal planar like the PF3. It's like we are having nitrogen here at the top and here fluorine, fluorine, and fluorine. Here is what geometry determines. Here is where geometry determines the polarity. Let me draw the bond dipoles. In PF3, each PF bond is polar because fluorine is way more electronegative than the boron. So we will draw 3 dipole arrows pointing from the P towards the more electronegative fluorine. But look what happens with the geometry because of the perfect 120-degree symmetry. In all directions, they cancel out completely. They cancel. It's like the 3 guys are pulling the boron equally. So imagine you are standing here and all your colleagues are pulling you, one from here and one from here and one from here. At the end, the pulling is canceled out. So there is no net result. You don't move from your place. The vector sum is 0. PF3 is non-polar despite having polar bonds. So the polarity is canceled out. The NF3 is different. Each NF is also polar, right? So this is polar and this is polar. Imagine that these guys are pulling you. This one, 3 of your friends are pulling you, but then fluorine is more electronegative than the nitrogen, right? 3 the pole arrows, the pulling is towards this one, this one, this one. So what is the net dipole? It's like you are standing here, one colleague pulling here, one colleague pulling here, one colleague pulling here. So where you will go? You will go down. 3 dipole arrows pointing from M towards each F. The trigonal pyramidal geometry is not symmetric. That lone pair on the top creates asymmetric distribution. The 3 dipoles pointing down don't cancel out. They add up to give a net dipole moment which goes down, which is away from the lone pair. So the rule, general rule, the symmetry leads to cancellation. The symmetry here leads to cancellation and makes nonpolar molecule. The asymmetry prevents cancellation and equals polar molecule. So statement for full credit, PF3 is trigonal planar, which is fully symmetric, causing the bond dipoles to cancel, making it nonpolar, which is while NF3 trigonal pyramidal due to the lone pair, which is asymmetric, preventing the dipole cancellation, making it polar. So let's check the rubric. We identified BF3 as trigonal planar, fully symmetric, identified NF3 as trigonal pyramidal, asymmetric due to the lone pairs, justified that the symmetry causes dipole cancellation and make nonpolar molecules, while the asymmetry prevents cancellation and makes a polar molecules. The 4 points are secured. Let's move to the next question, FRQ 7.